And in this video, we're going to be going over what I'm calling section 1.1, Undefined Terms, Definitions, Postulates, Segments, and Rays. So in this section, I'm really just going to give you an introduction to some of the vocabulary words that you're going to be seeing. Some of this may be review for you if you've taken geometry recently. So in geometry, an undefined term is a word which does not require any further explanation or elaborate description. It can be described, but it cannot be given a precise definition using simpler known terms. Right, so an undefined term, we have 3 undefined terms that we're going to cover today, but these are words that there's no way to break them down into any more simple terms than they already are. Right, so let's look at our 3 undefined terms. So in geometry, our 3 undefined terms are point, line, and plane. Right, so a point and a line and a plane. Right, so we're going to talk about these each individually. Then I'm going to give you some examples of what is a point in real life. What would we consider a point? What would we consider a line? And what would we consider a plane? Right, so let's begin with a point. A point refers to the idea of an exact fixed location. It has no size. You can think of it as a circular dot that's representing the location of the point, but the point itself has no size. We represent them by dots, little circular dots. We name them using capital letters. Some examples of a point include the tip of a pencil. Right, so down there at the very bottom, the little pointy, sharpened tip of the pencil. The corner of a cardboard box. A dot on a piece of notebook paper. So the tip of the pencil here, the corner of the cardboard box, or a dot on a piece of paper. Those are all representations of a point. Next undefined term is a line. A set of infinitely many points which are arranged in a straight path, and that path extends endlessly in opposite directions. Lines, similarly to points, they have infinite length, but they have no width or thickness, right? So we said that a point has no size. It's just a dot representing a location. Lines do have length, but they do not have width or thickness. Represent lines using double arrows, and we name them one of 2 ways. We can either use 2 points that are on that line, or we can give that line its own special name, and we use a single cursive letter. Right, so you may see lines written in one of 2 ways. You may see them written like AB with a double-sided arrow, or a line above it with double-sided arrows, or you could name it just the line. Let me try that again. Cursive letter L. So that was my attempt at a cursive letter L. Alright, so some examples of lines. An example would be the rung on a monkey bars, on the monkey bars here. So any of these rungs could be considered lines. Now this line in particular that I'm pointing at would not have infinite length. It would have a set length that was a number, but that is what we would consider a line in real life. Another example of a line would be the crease on a folded piece of paper. All right, so this crease here or this horizontal crease, those would both be considered lines. And the edge of the table here, so the edge of this table would be considered a line. Right, and then you could look at all four of the edges as four individual lines. So this left edge would be considered a line. The edge on the other side would be considered a line. The right edge is a line, and then this edge here is a line. So four separate lines. Our last undefined term is a plane. Are flat surfaces that extend endlessly in all directions. So unlike a line that only went in two directions, this plane extends in all directions. You can think of it as like the floor. Imagine you had a big empty gymnasium, so a big empty basketball gym. You can think of the floor as the plane. Have infinite length and width, but they have no thickness. Right? So we're not considering planes to be a certain thickness. They just have infinite length and infinite width. Planes are represented by a four-sided figure. I'll draw how we typically represent planes here. It's kind of like a rectangle, a sideways rectangle. Oh, that one. So here's our plane. Planes are named using 3 points that are on the plane, and they are not supposed to lie on the same line. So you don't want to pick 3 points that are in a straight line. You're going to pick 3 points which do not lie on the same line. It's okay if 2 of the points are on the same line, but you want at least one of those points to be on a different line. That we use for planes are cursive capital letters. So if we named the plane P, you would just do like a cursive capital P. I tried to make mine look a little fancy so you could tell it was in cursive. One example of a plane, you can think of a countertop. All right, so here we have a marble countertop. You could consider the top of this to be the plane. You could consider the side of the countertop to be a separate plane. A piece of paper, you can think of that as a plane. Artist's canvas, so that flat surface could be considered a plane. Now, the first thing we need to talk about are postulates. This may be the first time you've heard this word, or it may be the first time you've heard it in a long time if it's been a while since you took geometry in high school. But a postulate is a statement that we assume to be true. Right, so postulates are statements that we have to assume are true. But what is the purpose of a postulate in geometry? Postulates state relationships between our undefined terms, and that's going to help us understand them better. Right, so we found out that undefined terms, these are these simple sort of building blocks, and stating these postulates can help us understand what is a line or what is a plane. So they help us better understand our undefined terms. Postulates also establish some of the first principles upon which the entire field of geometry is based. Right, so These establish some of the very basics of geometry, which we're then able to build upon to establish more complex principles. Postulates also allow us to deduce new results. Right? So we are able to combine those postulates and then determine or deduce new postulates or new theorems, new axioms using those postulates. Some of the earliest records that we have of postulates in geometry come from the mathematician Euclid's book, The Elements. Here's a screenshot that I found online of one page in Euclid's book, The Elements. It is a collection of definitions, postulates, theorems, and proofs in geometry. This book was so important in geometry that they named an entire branch of geometry after him, called Euclidean geometry. So next we're going to talk about some postulates, 6 postulates in particular, all of which were found in this book, The Elements. This book was written in 300 BC, so over 2,000 years ago. So we can use postulates, combine them with definitions to create theorems. I'm going to give you a brief definition of theorems, and then we will get into our 6 postulates that we want to discuss. These are results that we deduce from a combination of our undefined terms, other definitions, along with our postulates. The purpose of theorems in geometry is that they serve as the building blocks for solving more complex problems and understanding complicated geometric concepts. And theorems, once they are proven, are held to be true, and then they can be used in proofs of other theorems or other axioms, which are sort of like miniature theorems. So let's discuss our 6 postulates for today's lesson. The postulates are, again, going to be statements that we have to assume are true, and in each one, I'm just going to give you a little brief overview of what we know about geometry, or what do we know about lines, points, and planes. This postulate. All right, so the first postulate we're going to talk about today, I'm calling it postulate 1, and that postulate says every line contains 2 distinct points. Now this may sound really simple to you, and it is a simple concept, but it's actually a powerful concept that allows us to solve a ton of problems in geometry and in algebra. All right, so a line contains a point. We say that that point is on the line. All right, so you can see here the points A and B are on this line. We already learned that there are a couple of ways that you can notate or name lines. You can use 2 points together with a double arrow over the letters. So we could do AB with the double-sided arrow over the top. It's important to note that the line AB is the exact same line as BA. So when we're talking about lines that have arrows on both ends, the order of the points that you list does not matter. Right, so the line AB is the same as the line BA. Now we also learned that you can name lines by using a single letter in cursive. So if you decided you did not want to use this notation here, you could rename this line something like a cursive L. So if you wanted to name it, you don't have to use L, you can use any lowercase cursive letter, whatever your favorite one is. You could call it F. Right, so as long as it's a cursive lowercase letter, any letter is fair game. The last thing I want to note before we move on to the next postulate is that this line, although I have identified points A and B here, this line contains infinitely many points. So there are infinitely many points in between A and B on this line. Those points might be integers, so positive or negative whole numbers. They might be decimals, like 1.2, 7.005, or they could also be fractions, or even things like square roots, like square root of 4. All right, so there are infinitely many points on this line. Postulate 2 says, 2 points are contained in one and only one line. This postulate is just a formalization of the idea that 2 points determine a unique line, which is a concept that you've probably learned in algebra. So I'm sure you can remember or recall using 2 points on a line to find the slope. All right, so this postulate is just a formalization of that concept. All right, so if we have this line here, AB, there's only one line that goes through these 2 points. There's no other way to draw this line. For example, if I draw the line like this, you can see that is clearly not possible or not correct. That is a curve. That is not a line. Lines are straight. Curves are not straight. All right, so 2 points are contained in one and only one line. There's no other line that you could draw that goes through these 2 particular points. Our next postulate says, if 2 points are in a plane, then the line containing these points is also in the plane. Right, so if you have a plane, 2 points, right, and then we draw the line connecting those 2 points, then that line must also be in the plane. Right, so again, if you have a plane and there are 2 points in that plane, if you connect them with a line, then that line must also be in the plane. So even though we don't have it represented here, remember that this plane continues infinitely in all 4 directions. Right, so this plane continues on up, to the right, down, and to the left. Right, so the plane extends endlessly in all directions. Now, this postulate gives us 2 important vocabulary words, collinear and non-collinear. Points are said to be collinear if there is a line containing all of the points. So in this example here, A and B would be considered collinear because they are on the same line. Points are said to be non-collinear if there is not a line that contains all of the points. So for example, if we had another point out here, let's call it C, you could say that A, B, and C are non-collinear. So they are not all on the same line. Another example of collinearity or non-collinearity can be shown here. So suppose that we have this line A, B, and C are points that are on the line. We have D, the point D, which is out here by itself. It is not on the line. So we would say that A, B, and D are non-collinear. They are not on the same line. A, B, and C are collinear. They are on the same line. All right, so you could come up with more examples of non-collinear points. You could do C, B, and would be non-collinear. They are not on the same line. And then I think you have one more you could do. A, C, and D, non-collinear. They are not on the same line. So even if two of the points are on the same line, if at least one of the points is not on the line, then they're considered non-collinear. Postulate 4 says, 3 non-collinear points are contained in one and only one plane, and every plane contains at least 3 non-collinear points. All right, so let's talk about what that means. The first part says, 3 non-collinear points are contained in one and only one plane. All right, so what that tells us is that this unique and distinct plane that contains these 3 points, and there's no other plane that's exactly like this one. Just like with the line, this is a unique plane. And the last part of the postulate says every plane contains at least 3 non-collinear points. What this tells us is that this is guaranteeing that a plane is going to consist of more than one line. Right, so example, A and B could be considered collinear. You could draw a straight line through those points. A and C could be considered collinear. You could draw a line through those points. So that's already 2 lines, 2 separate distinct lines. You could do another line here between B and C. That would be a separate line, so a 3rd line. But A, B, and C are non-collinear. You cannot draw a straight line through those points. Last thing I want to talk about is this point over here, D, that is off the plane. Points are said to be coplanar if they all lie on the same plane. But if there's a point that is off of the plane, like D in this example, then we would say the points A, B, C, and D are non-coplanar. They are not all on the same plane. Right, so points are said to be non-coplanar if there's not a plane that contains all of those points. Right, so A, B, C, and D in this example are non-coplanar because they do not lie on the same plane. 5th postulate says, in space, there exist at least 4 points that are not all coplanar. All right, so let me tell you what space is. Space, all right, so let's write this down. Space is defined as the set of all points. So space is defined as the set of all points. So in space, there exist at least 4 points that are not all coplanar, that are not all on the same plane. And this is important because this assures us that space is not just a single plane. Right? So space is not a flat plane. That is to say, space is 3-dimensional. Here's an example of a 3-dimensional space. So you can see, let me change over to my laser. So you can see we have the plane P here in red. And then we also have the second plane Q in blue. Those those planes intersect on a line M. And that is how we represent 3-dimensional figures in space. All right, so that is how we represent 3-dimensional problems in space. The last postulate that we will cover today involves the real number line. It's called the postulate. It says every line can be made into an exact copy of the real number line using a one-to-one correspondence. Now you've probably heard the phrase one-to-one correspondence in algebra. A one-to-one correspondence just allows us to match up one point on one line with another point on another line. So it's not going to match one point from the first line with multiple points in the second line. So it's going to be a one-to-one correspondence. This postulate is really important. It allows us to draw a lot of conclusions about plane geometry, and it also allows us to find the lengths of line segments. So let me show you first what that one-to-one correspondence looks like. So let's say we have this straight line here. We're going to call it L, and that line is going to represent the real number line. We can draw a second line. It's just an exact copy of the first line L. And here we're going to label some of the points on the line. You can see I've labeled from -3 to 3, and here I'm only labeling the integers. Each of these little points on this number line are called coordinates. All right, so each of these points on the line is called a coordinate. So let me write that down. So these are called coordinates. Coordinate is important because that's what allows us to find the length of a line, or the length of a line segment, which we'll talk about in a minute. So let's say that I'm going to grab a specific point or a specific coordinate on this number line. So the point A on the number line represents the coordinate -2. All right, so A is just a representation of that spot on the number line, but the coordinate is -2. You'll notice that I've only labeled the integers on this line. The real number line consists of all real numbers. That includes decimals, fractions. But it would be impossible for me to label all of the points on the number line since the set of real numbers is infinite. So what the ruler postulate tells us is that all lines have infinitely many points. All lines have infinitely many points and are all infinite in length. All right, so the lines, again, we're calling a line this line with the double-sided arrow on it. These are infinite in length, and they contain infinitely many points or infinitely many coordinates. So let's talk about some of the results that follow from the ruler postulate. So we can use the ruler postulate to determine the distance between 2 points on a line. And this is the formal definition. It's actually really easy to find the distance between 2 points. And it says if x1 and x2 are points on a line, the distance between those points is, it says d equals the absolute value of x2 minus x1. All right, so for example, if you have a line, let's just mark, let's do -2 and 1. This A and B. So let's find the distance between those points. So we would have D, the distance, equals the absolute value of x2 minus x1, so we need to label these. It doesn't matter what order that you label them in, because of the absolute values. That's what allows us to not have to worry about the order. But let's call this one x1 and this one x2. So the distance equals the absolute value so you see where I'm looking at. The distance equals the absolute value of x2, which is 1, minus x1, which is negative 2. Close the absolute values. All right, so now the way absolute values work is you simplify the inside first. 1 minus a negative 2, that double negative turns into a positive. 1 plus 2 is 3. So absolute value of 3. The absolute value of 3, that's just the distance that 3 is from 0 on the number line, and that is just 3. All right, so the distance between those 2 points is 3. All right, so let's talk about line segments. Line segments are given the definition below. It says, if A and B are 2 points on a line L, then the line segment determined by A and B is written as AB with a line over it, notice there's no arrows, or BA with a line over it, no arrows. So again, the order doesn't matter here. You're talking about a line segment. It's going to be the same length whether you go from A to B or if you go from B to A. A and B are the endpoints of that line segment. All right, so this line segment would look something like this. All right, so you have a dot on the end instead of an arrow. All right, so you have a dot on the end instead of an arrow. That's indicating that that line ends right there at A, and then same thing over here, the line ends right there at B. The length of a line segment can be determined using that same formula from the previous slide, and you're just going to let A and B be the points x1 and x2. The last thing we need to talk about with line segments involves when you have 2 line segments that have the same length. So when 2 line segments have the same length, we say that those lines are congruent. Not equal, but congruent. All right, the symbol for congruent, you can see that below. So suppose we have 2 line segments, AB and CD. If those 2 line segments have the same length, we say AB is congruent to CD. All right, so this symbol in the middle is an equal sign with a little tilde above it. You read that as is congruent to. Now, some textbooks may also use the following notation. So instead of using this equal sign with the tilde above it, they will just say AB. Notice that there's no line above it. AB equals CD. Now the lines are not equal. They may have different points on those lines, but they are the same length. So here we would still read this as line segment AB is congruent to line segment CD. If we have 2 lines drawn and we want to indicate that those lines are the same length, the technique is slightly different. So suppose we have these 2 line segments AB, so that's the line segment on the left, and then a separate line segment CD, and these line segments have the same length. We would indicate that those line segments have the same length by using tick marks. So whenever the 2 line segments have the matching tick marks, that would mean that those line segments have the same length or they are congruent. If you have a picture or an object that has multiple pairs of line segments that are congruent, then you're just going to use double tick marks or triple tick marks. So here, let's say that we have another set of congruent line segments, EF here on the left, and then GH on the right. We would indicate that these two line segments are congruent by using double tick marks. All right, so you would match up, okay, this one has 2 tick marks, this one has 2 tick marks. Those two must be congruent or have the same length. The last thing I want to talk about today in this video is a ray. A ray is a portion of a line that has one endpoint and extends indefinitely in one direction. All right, so here's a picture of a ray. All right, so you can see that it has an endpoint here, A, but it is extending indefinitely in the other direction. All right, so B is just another point on the line, or on the ray, I should say. B is another point on the ray. You want to try to be precise here when you are notating this. All right, so here is the notation for a ray. You can see it's A, B with a line above it with a single arrow. You want to put the endpoint on the left and then the other point listed second, and then make sure on that line above that your arrow is pointed to the right. All right, so I hope that you feel a little more confident about some of these vocabulary terms that we've went over in this video. And what I would like you to do now is go onto D2L and complete the section 1.1 homework. All right, thank you so much, and I'll see you in the next video.